Hi there, Physics Higher. This is Mr. Long, and this is your lesson for week beginning Monday, the 22nd of February. Now, you are getting a new piece of content every week with a homework and questions, and the majority of you are kind of keeping up with the work, which is great and great to see. But many of you are still struggling with it and not necessarily getting it in time. What I want to say is don't need to worry too much about meeting all the deadlines. As long as you're getting as much work done as you can, then that's all we can ask for. Just do your best. And obviously, the more work that you get through, the less catching up we'll have to do when we get back to the school building. But I don't want anyone worrying about the deadlines so much as just trying to get through everything in order. A couple of people are trying to do the recent stuff and then forgetting about the old stuff, but the old stuff needs to be done in the right order for you to be most benefit. If you get any issues, please just email your class teacher. Myself, Mr. Huggins and Miss Gibson are all very happy to help you and support you and talk you through any problems that you've got, and just make sure you take your time and do the best you can. One of the things about the homeworks, the official homeworks, is that we want you to self-mark them and get them back to us, upload pictures, and that way we can feed back to you. Some people aren't doing that either, so can you try and do that as best you can. Okay, so this week we're going to move on from the spectra and light stuff and the photoelectric effect, and we're going to talk about waves more specifically now, sort of light waves in particular. And before we get into that, I want to go through some terminology that we've got. So the first piece of terminology I want to talk to you about is the word medium. Now, medium, I often talk about medium in classroom as if you're going to a medium, you're communicating with the dead, and somebody's a medium for you to talk to people that are dead. And that's the way I like to think about it. It's something that passes through. So if you're speaking to spirits beyond the grave, they're talking to you through somebody else. So that's the medium. So the medium is something that passes through. When we talk about the medium for waves, it's a material that a wave can travel through, can pass through. So different mediums allow different waves to pass through them. For example, in the diagram there, radio waves can pass through brick walls, but light waves cannot. So a brick wall is a medium for radio waves, but not a medium for light. Glass, on the other hand, light waves travel through glass, and so do radio waves, so glass is a medium for both radio and light waves. Now we're going to talk about light mostly in this part of the course, and the common mediums for light are air, glass, perspex, which is that plastic that we use the little semicircular blocks and the rectangular blocks from, a vacuum, which is space, which is no air, and water. We're going to make a vacuum and air quite similar. I'll explain that in a minute, but these are common mediums that we're going to be using. The second piece of terminology that we're going to look at is the word density. Now, you don't really need to know a lot about density. It's mentioned at National 5 and again at Higher, but it's to do with the materials and the mediums that waves are passing through. So we use the word density to describe the properties of different mediums. And the density of material is how tightly packed the particles of that material are packed together. Now if you look at the diagram, this is the particles inside the mediums. Gases, they're not that tightly packed together. Liquids, they're more packed together, and solids are even more packed together. And that means that a gas is less dense than a liquid, which is less dense than a solid, or solid is the most dense, gas is the least dense. Now there is a difference between physical density and optical density for waves, but we're not really going to go into that in this lesson. But just when we talk about it, we'll talk about a more dense substance and a less dense substance. Our least dense substances are air and a vacuum. Vacuum being even more less dense, but the air are a vacuum at one end, and at the other end you've usually got glass, and then water is somewhere in between. The last piece of terminology we need to be 100% with is the word normal or normal line. Now we've met this at National 5, and we've even met it in second year or third year. And the normal line is this line here on any diagram, any wave diagram that we do. And it must be added to all wave diagrams. Now it's an imaginary line that we put onto the diagram. This would be a surface or a boundary or whatever we've got, or a mirror, and we must add a normal line onto that. And the angles must always be measured between the normal line and the ray of light. We never measure this angle in here or this angle in here. It's always the normal line to the ray of light we measure the angles between. Now the normal line is at right angles to the surface or right angles to the boundary, and it is always originates here at the point where the light hits the surface. So we draw that normal line up and down. It's at right angles to the boundary, and it starts there at that point and goes up, and it can pass through to the other side as well. It's really important that we always measure these angles in here and don't consider these. That's a very, very, very common mistake that people get wrong. Okay, a little bit of revision from that 5. It's just about reflection. Reflection is important because we are going to talk about reflection in a bit more detail. Now, it's just so we get the terminology right. You've got a normal line there, you've got a surface, you've got an instant ray. An instant ray means the ray coming in, and you've got a reflected ray, which is the ray coming out. You have an incident angle, so that's the angle the instant ray makes with the normal line, and you have a reflected angle, which is the angle of reflection, which is this one here, angle of incidence, angle of reflection, and the law of reflection is that the angle of incidence equals the angle of reflection. And we'll come on and talk about that in more detail and how we're going to use that soon. Now the other piece of terminology that you would have done in Nat 5, but we're going to look at in a lot more detail just now, is refraction. Now, refraction, reflection, and we're going on next week and talk about, or maybe the week after, I'll talk about diffraction and interference. These are all properties of a wave that makes a wave a wave. If it doesn't reflect and refract, then it's not a wave. So this is when I'm saying it's a property of all waves, including light. So refraction is the change in wave speed and wavelength as light passes between mediums of different density. The frequency always stays constant. So the definition of what refraction is has got nothing to do with changes of direction. It's just the change in speed as the wave goes from one medium into another. This changes the wavelength as well from one medium into another. Frequency is the same, so the colour stays the same. Now the change of direction comes about because the wave is changing speed. Now I did this in my class, I remember, at Nat 5. If you have a wave coming in and part of the wave slows down but the rest of the wave is going at that fast speed, then that causes the wave to turn. Now there's descriptions of this in your textbook, and have a little look at it, but it's the wave speed slowing down that causes the turning, the change of direction of that wave. Now this point here, if the angle between the normal is 0, so if the ray of light comes straight in, it will go straight through. Now it still refracts. So if you've got a boundary and a wave coming straight into that boundary, it won't change direction, but it will slow down and it will change wavelength, but it won't change direction. So refraction is still happening when rays of light pass straight into substances with 0 angle of incidence, but they are not changing direction. If the angle is greater than 0, then there will be a change in direction. Now the top diagram here shows that when it goes from a less dense medium, such as air, to a more dense medium, it changes direction, what we say, towards the normal. This angle here is larger than this angle here. This is the ray of light changing direction towards the normal. In the bottom diagram here, it's a more dense medium, glass, going into a less dense medium, air, and you can see there that the angle gets bigger. So what we say is it changes direction away from the normal. Now sometimes you hear the word bending being used. Now it's important you don't use the word bending, because bending suggests that the ray of light is curving, or curves or bends. If there's a bend in the ray of light, then there's a curve in it. That's kind of a normal way of thinking. So if you use the word bending, it's very easily confused with curving, and it's not curving. It's just changing direction. So the light passing from a less dense to more dense medium reduces the wave speed and wavelength, so that's what happens with refraction is, the wave speed slowing down, and so is the wavelength's changing as well. The wave changes direction towards the normal, so the wave speed gets less and the wavelength gets less, frequency stays the same. Other way around, the wave speed increases and the wavelength increases, but again it changes away from the normal and the frequency is constant. Now, the amount of change in direction is often referred to as the amount of refraction, and again it's not important not to mention the word bending when we're doing this. So there's an experiment. This is taken from BBC Bitesize. You can go and have a look at the BBC Bitesize website and it talks you through this in a bit more detail if you want. You've got to be familiar a little bit with how we measure, we do an experiment on this refraction. It's something called refractive index, but we're going to go on and talk about refractive index in the next slide. So what you'd have here is a semicircular block of perspex or glass. You shine light into one side, into the air side, and the light comes through on the other side, and you're measuring the angle here and the angle here, and you'll see in a diagram that this angle here is definitely larger than this angle here. And if you change the angle in here for between 20 and 80 degrees, change all these angles, and this ray of light will move gradually further around, you will measure different angles in here. Now, one of the things it doesn't say in the diagram is why do we use a semicircular block? Well, if you look closely, as the light comes to this boundary here, it's always at right angles to this curved part, so it doesn't change direction and allows you to draw the ray of light as it comes out the glass or the perspex. Now, if you then take all your data of all the angles before and all the angles after, and you plot, you make them sine, so sine of the angles, and you plot that, you get a straight line. And that means that there's a constant relationship there between the sine of the angle of incidence and the sine of angle of refraction. And that constant relationship, like we've done in the past, is known as your refractive index. Now, we're going to go on and talk a bit more about refractive index, but this just shows you there is a relationship between the sine of the angle before, the sine of the angle after, or the sine of the angle in the air and the sine of the angle in the substance, that we're going to go into in a bit more detail in a second. So, this is known as refractive index. So it takes place, depends on the property of the medium called refractive index. So the amount of refraction that takes place is to do with the refractive index of that medium or material. Now, if you want to measure the refractive index, we need to consider light going from air or a vacuum into that material. And that is known as the absolute refractive index of the medium. So if you're going from air or a vacuum, now I'm probably just say air from now on, but we could use a vacuum, into the material, then it's the refractive index of that material. I keep saying material, but it's actually medium. Okay, so refractive index is the ratios of the sine of the angle in air over the sine of the angle in the medium. The change in angle, wavelength and wave speed can all be used to calculate refractive index. So this is this bottom part here. It's not just sine theta 1 over sine theta 2 or sine theta air over sine theta medium. It's the wavelength in the air divided by the wavelength in the medium and the speed in the air divided by the speed in the medium. The frequency is always constant. Because the speed is changing and the wavelength is changing and v equals f lambda, frequency has to stay the same if you want to think about it that way. The physics data sheet refers to all the mediums as 1 and 2. So this is what you get, sine theta 1 over sine theta 2, but it's much easier and much easier to deal with questions if you don't think about it as sine theta 1 over sine theta 2. You just think about it as sine theta air over sine theta medium, and the theta air is always the largest angle. Now this is unique for that boundary, but it works for all the questions you're going to have. So when you do your questions in this, it's important that you give them a go. Okay, now just in your data sheet, you're given a number of these absolute refractive indices, and it allows you to get the number without having to go through all the calculations, and sometimes you'll be asked to use their absolute refractive index to work out different values inside questions. But just a point to note here is that if you change the wavelength of the light, you're going to change the refractive index because different wavelengths refract different amounts. So it's important to note that in the datasheet you're using a wavelength of 589 nanometers. And that's fine if you're not really that concerned about the wavelength of light. But if you're told the wavelength of light and it's not 589 nanometers, you can't use these refractive indices. So just be careful of that. It's just a point to note just in case there's something that comes out from that. That's just a definition of the absolute refractive index. which is a medium, is of a medium, is defined as the ratio of the speed of light in a vacuum to the speed of light in the medium. It's just a point to remember. Right, at this point in the lesson, you normally go away and do refractive index questions. In fact, there's a whole section of refractive index questions using the formula that you had in the last slide. The best thing is you go away now and you try those questions, check the solutions at the back and talk to your teacher, or go in a class call if you've got any issues. The next part of the lesson is on critical angle and internal reflection. That's got a separate wee bunch of questions on it. So the best thing you can do right now is pause, go away and try some questions, and then come back and do the rest of the video. I'm just going to carry on just now, and then you can pick this up later in the week. It's probably the easiest thing to do. So, going a wee bit further, and from what I said in the last slide, to say that the light, every wavelength refracts a different amount. So if you refract white light, it will turn into its separate colours. So if you refract white light, you will get the violet, the blue, the green, the yellow, orange and red, and it will turn into a spectra. And that's one way in which we get the visible spectrum, or we get our line spectra as we refract the light, and then that gives us that. If you used a prism in class to refract the light, you've seen the different colours, and that's because different wavelengths refract different amounts. Now, blue violet light refracts the most, so you'll see it's further refracted around here, and red light refracts the least, so it doesn't refract as much. It's just important that you realise that. And if you're talking about violet light, and then the question asks you to change to red light, it's important you understand that the red will refract less than the blue light refracted. The smaller the wavelengths, the higher the frequencies, the more refraction that takes place. And obviously the inverse of that is also the case. Okay, critical angle. So as light passes from a more dense material into a less dense material, it changes direction away from the normal. Now we did that a few slides back. But as you increase the angle going in, the angle of incidence here, you'll notice the angle gets bigger and bigger and bigger on the other side till eventually it gets to 90 degrees. Now if you have a ray of light going into a substance and the angle of refraction has changed so much that it's 90 degrees, you've reached a tipping point known as the critical angle. And it's important that you know that at that situation where the angle of incidence is equal, it results in an angle of refraction of 90 degrees, that tipping point, something happens after this, which we're going into the next slide, but that tipping point is known as you're at the critical angle. So there's a definition for that which I've given you here in red, is the critical angle of a medium is the angle of incidence that results in an angle of refraction of 90 degrees. Now here's just a little diagram showing you what's happening. So if you've got normal refraction like this, it changes direction. When you reach the critical angle, this is what happens, and that's a 90 degree refraction angle. Now we often use a semicircular block to demonstrate this in class. Again, it's so that we can shine light into a block without it having any refraction at this boundary. So we would do that in class, and I'll try and get a YouTube clip of that if I can onto the assignment for you. So the critical angle is linked to something called total internal reflection. After that tipping point, after the critical angle has been reached, up to the critical angle, refraction takes place, and you've got this angle getting bigger inside the medium. Beyond the critical angle, then it can't really refract any more than 90 degrees. So up until the critical angle, it just refracts through, like this diagram here. At the critical angle, there's a refraction of 90 degrees. As soon as you go above the critical angle, it reflects inside the material rather than refracting out with the material. And that angle here, this tipping point critical angle, is linked to the absolute refractive index of the material by this formula here. So this angle theta c is the critical angle for the material. Anything above that results in total internal reflection. But the critical angle itself is the point at which refraction is 90 degrees. Now, we use this formula here for n, absolute refractive index of the material, is equal to 1 over sine theta c. And you'll get some questions in that. It's important you do some of those. There's some more of those questions in the booklet as well. Right, Last thing I've got here is a little worked example taken from the past paper. This is from 2019, it's question 11, you're given this diagram here. Now Mr Huggins is quite proud of this question because he made this question up for the exam, so he quite likes it. I didn't know that before I picked it. And you've got this diagram here of diamond material, and you've got light coming in here. It's refracting into the diamond. You should be able to see there that there's a bit of reflection happening there. It's totally internally reflected in here. Hits here, it's totally internally reflected in here again, comes back to there, and it's refracted out of the diamond there. And the question asks you, so a ray of monochromatic light is instant on a diamond at an angle of 49 degrees. Now monochromatic light means single coloured light. I might go back and change the slide in that earlier. The refractive index of diamond for this light is 2.42, and calculate the angle of refraction theta. So you're asked to calculate this angle here of refraction theta. So 49 degrees is what the angle is in air, and you're asked to calculate the angle inside the diamond. So you use your formula, n is sine theta 1 over sine theta 2. Now remember that's going to be sine in air over sine in diamond, so the sine in air is 49 degrees, the n is 2.42, and you're asked to work out theta 2, rearrange, do sine inverse, and you get 18.2. Now this is a slightly different way of doing it with two refractive indices, not what I've showed you to do it, and you don't get that in the formula sheet, but that is how I'd expect you to do it, and that would be 3 marks. Second part of the question is calculate the critical angle of the diamond for this light. Use the formula sine theta c is 1 over n, or n is 1 over sine theta c, it doesn't matter. You plug it in, the 2.42, and rearrange for theta c, and do sine inverse, and you get 24.4. 3 marks for that, 3 marks for that, nice and straightforward, and you'll get questions similar to this in the homework which I'll be giving out next week. Any problems in any of this, please join the class calls. Mr Huggins and myself are running class calls for our classes, and also there's the general class calls on Thursdays for everybody, including Miss Gibson's class. I really want you to come on the class calls. I'll go through the PowerPoint again if you want in the class calls. I'll answer any questions, I'll do some worked examples, but we're not getting enough people coming in the class calls. So please come in either Thursday, or if myself and Mr Huggins is doing it, you might get another opportunity during the week. But there is a class call for everybody. So please come on and give it a go. And even if you just sit and listen, it's really good to get some extra help. And again, if you're struggling, just ask, just talk to us, and we'll be able to help you with anything you're struggling with. Okay, good luck for this week.